And I can say again, hello, everybody. Our speaker today, the semester opener, is Adam DOR-ON from the University of Copenhagen, and it's going to be about operator algebras and subproduct system. By example, like I really like this title because it's one of my favorite books by Davidson, Sister Algebras by Example. So it rings a bell. It rings a very nice chime, actually. So Adam, the floor is yours. Take it away.
All right, wonderful. This is an incredible honor for me. First of all, I thank you, Piotr and Richard and the organizers for having me give a talk in your seminar. I want to tell you about my journey through subproduct systems and their operator algebras, okay? And so for starters, I would like to tell you a little bit, I want to start with examples, okay? And I want everything to sort of be motivated by examples, okay? And so suppose that D is a natural number, and let CZ be the algebra of polynomials in commuting variables Z1 up to ZD. Right, Z alpha, this is going to be just Z1 alpha 1 all the way up to ZD alpha D, where alpha is equal to alpha 1 up to alpha D is in n to the D. And now a classical space that's sort of been studied extensively is the Drury-Arveson space. H2D, and is the completion of polynomials in decommuting variables with respect to the following inner product. It's going to be Z alpha Z beta equals delta alpha beta times the following weightage. Okay, and this is for alpha and beta in n to the D. Okay, and the point is that you look at the space, and this is really a space of functions. You can think of, or we view any function in H2, any element in H2D as an analytic function.
This is not at all symmetric in alpha and beta.
Please.
What?
You mean? Right? Either alpha is equal to beta, and then you have this weightage here, or if alpha is different from beta, that's equal to 0.
Okay, right? Yeah. Okay, yeah. So in fact, it is symmetric in alpha and beta.
That's right. Yes.
Yeah, I see. Okay, good. Yeah. Good.
If alpha is different from beta, they're orthogonal.
Well, it's 0. Yeah. Yes. Okay. Yeah. Right. Okay. Good. Thank you.
And so the functions are given by f of z is equal to the sum of alpha and n to the d of some c alpha times z alpha. So you can think of these as functions where you have this convergence, this uniform convergence here. Okay. And on this space, you have sort of natural multiplication operators. So let mz be mz1 all the way up to mzd. The d-tuple of coordinate multiplications, coordinate function multiplication, given by mzi times p at z is just going to be zi times p at z. This is for any polynomial in decommuting variables. Okay, then this tuple mz is a row contraction. So that means that if you look at this mz1 all the way up to mzd as an operator from h to d into h to d, that's a contraction. Okay. So now it turns out that somehow this is the biggest row contraction. And every time you have a row contraction, then there is a sort of map that sends this particular row contraction onto your specific one, okay? And then you can sort of start asking for your row contractions to satisfy some homogeneous polynomial relations, okay? So if I is an ideal, and I want it to be a homogeneous ideal, then I times h to d is invariant for these MZs.
What do you mean by a row contraction? You say you have a row contraction, what does that mean?
It means that as an operator from h to d to the d, direct sum with itself d times,
Yes.
back into hd,
Yes.
that's a contraction.
What you mean it's norm reducing? Is that what you mean? What do you mean by this?
It means that as an operator, right?
Yes.
That you sort of you get a vector of vectors, right?
It's norm reducing.
Norm reducing. Okay.
That's what you mean. It's norm reducing.
Norm non-increasing, I would say.
Yeah,
Oh,
yeah,
norm non-increasing.
Yes.
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 Okay.
Okay.
It's norm non-increasing. Okay.
Norm non-increasing.
Yeah. Okay.
Okay.
All right. All right.
And it
Good.
takes a row into a scalar, right? This is the idea.
I'm sorry, Piotr?
And it takes a row of elements in this H to D into a scalar, just one element in H to D. That's
It takes a column. You think of H to
sorry,
D
a column. Yes.
as a column, and then you multiply it as you would matrix multiplication.
Exactly.
And then you get some vector in H to D.
Yep.
And that should be a contractive operation.
Exactly. So contraction is explained by this norm non-increasing, and why
That's
row?
right.
Well, because this is like a matrix multiplication.
That's right. Yeah.
I have one question, Adam. Does the fact that they commute have anything to do with it?
The answer is no.
Okay.
And we will get to that actually. Okay. And so whenever you have a homogeneous ideal, then you can multiply this ideal, as functions by H to D. You can close it up and you get some invariant subspace for MZ. Okay. And if you look at the ortho complement of that subspace, that's a co-invariant subspace for MZ. That means for each one of the MZIs, right? So, and we get that Fi, this is H2D, ortho, the complement of IH2D in H2D, that's a co-invariant subspace. And we compress the original tuple MZ1 up to MZD to this subspace, okay? To get a new tuple, it's S, which is equal to S1 up to SD. It's given by P Fi MZ1 restricted to Fi all the way up to P Fi MZD restricted to Fi. And now what's nice about this new tuple now is that this new tuple is the universal tuple for commuting row contractions that satisfy the constraint in the ideal I, or the homogeneous relations in I. Okay, so let me write that down then. So first of all, for any polynomial in I, we get that PS is equal to 0. And S is universal such. Okay. So that means if you have T, some other row contraction that satisfies the relations in I, then really what I want to say is that you can generate a non-self-adjoint algebra from S, and you can generate a non-self-adjoint algebra from T, and there would be a quotient map from the one generated by S to the one generated by T. Okay? And these algebras are algebras of functions, right? Of holomorphic functions. Okay. So for this ideal of homogeneous ideal inside polynomials and commuting variables as above, we define the variety of the ideal. It's those elements in the D complex ball that are annihilated by all polynomials in the ideal. Okay, so this is sometimes called a homogeneous variety, and we define the sort of boundary of the variety. So this, I denoted this by VI. So let's change that to V sub I. This is the intersection of the boundary of the D ball, or the sphere, with the closure of VI. Okay. And now I want to get to a fine point, and this is Arveson's essential normality conjecture. And what it says is that for any I and J between 1 and D, the star commutator SI Sj star minus Sj star Si is a compact operator, or is in the compact operators on this F sub I. Okay. So in other words, if you quotient out by this ideal of compact operators, you get a tuple that is normal, a normal tuple of commuting row contractions, a row contraction of normal operators. Okay. Commuting row contraction of normal operators. And then I should probably mention a refinement due to Douglas says, whoops. That S is P essentially normal. In the following sense, that SI Sj star minus Sj star Si is in the Schatten P class, where P is greater than the dimension of the variety. Okay. So let's talk about some known results for when this essential normality has been established, and then maybe we will say some reason for why this is interesting from the point of view of geometry. Okay.
What is the Hilbert space on which all this is happening?
This is happening all on Fi. Fi is a subspace of H2D. Okay, it's the ortho complement of I times H2D. Does that make sense?
Is it a Hilbert space? Or my
It's
question
all
is,
Hilbert spaces, yes.
so you're saying that this F sub I is a Hilbert space?
It is a Hilbert space, yes. F sub I is always a subspace of, or in fact, it is equal to H2D, the ortho complement of I times H2D in H2D. That's always a subspace of H2D. Okay? Does that make sense?
How is that a Hilbert space?
How is that a Hilbert space? Well, it has an inner product. I guess it's closed. Maybe I should say it's closed. It's a closed subspace of a Hilbert space, and that means it's a Hilbert space. Yeah. I guess
So
that it's closed.
we're
Every
talking about-
ortho complement is closed. So that's a Hilbert space.
We're talking about bounded operators on this Hilbert space.
That's correct. That's correct. All right. So let's see some known results where this essential normality has been established. In fact, in most of the results that I will mention, p-central normality was also proven. Okay, so first of all, this was established for monomial ideals by Arveson himself. All my ideals here are homogeneous. This was in 2005. Then for principal ideals, or when D is less than or equal to 3 by Guo and Wang, 2008. For varieties, that are unions of finitely many subspaces, subspaces intersected with the ball. This was done by Kennedy and Shalit. I think this was 2012. And the sort of best, or you know, the sort of biggest advance in the verification of this conjecture was established by Englis, I think that's how it's pronounced, and Eschmeyer. So this is for varieties smooth away from 0. Okay, so this is, and Eschmeyer. This is, I forgot what year it is, but it was after. Okay, and whenever you talk about the varieties, you have to be careful because that puts a condition on the ideals. It forces your ideals to be radical. So you should imagine the Hilbert, Nullstall, and Satz in the back of your head, right? There's always a correspondence between radical homogeneous ideals and these homogeneous varieties. But for this correspondence to go through, you need to require that your ideals are radical. So this is for radical ideals. Okay, and so I want to look at this conjecture. This is sort of my starting point. I'm interested in this conjecture, and I want to know how can I reformulate it in a way that generalizes, okay, to other contexts. So the conjecture is equivalent to having a short exact sequence like so. So you have your copy of compact operators on Fi. You have a Teplitz algebra, which I'll define shortly, and you have continuous functions on the boundary of the variety, which I've defined earlier. It's just taking the variety and intersecting it with the boundary of the D-ball. Okay, and what is this Teplitz algebra? I'm going to define several C-star algebras now. So the Teplitz algebra is the C-star algebra generated by the identity together with S1 to SD, these compressions of multiplication operators. And I'm going to define another non-self-adjoint algebra. It's AI. This is just the algebra, norm-closed algebra, generated by the identity S1 up to SD. And I want to define a Kuntz kind of algebra, right? So a ratio by compact operators, if you may. So this is Ti modulo the compact operators. Okay, and then Arveson's essential normality, at least you can say that that's equivalent to the Kuntz quotient, this OI coinciding with continuous functions on the boundary, because then OI would be abelian, and that would force your SI stars all to commute. Okay, so that's the formulation of essential normality that I want to look at. It's the coincidence of OI with continuous functions on some boundary. Okay. And so I want to mention, okay, so now I want to make a definition. And this is the definition of subproduct systems. Okay, and it's a definition that's due to Shalit and Solel, but it goes back to a definition of Bhatt and Mukherjee. They defined it as something called inclusion systems. Subproduct systems were initially used for classifying completely positive semigroups of automorphisms on B of H that are with continuous time parameter, or with real time parameter that has some sort of weak type continuity condition. Okay, and these are related to Arveson's E0 semigroups, if you know what these are. Okay, but the definition here is just for discrete semigroups, or rather for just the natural numbers. But I have to say that the definition for these were sort of motivated from the study of E0 semigroups and completely positive semigroups. So let omega be a countable set.
I want to ask a question about your short exact sequence.
Yes.
Where is the difficulty here?
The difficulty.
Yeah, where is the difficulty?
The difficulty is showing that the quotient between OI to C of the boundary, that quotient is injective. That's the difficulty. That's in fact equivalent to Arveson's essential normality conjecture. Okay.
So in the exact sequence, where is the problem?
There is no problem with the exact sequence. The exact sequence, you only have it when the conjecture is true.
Yes. So if you want to prove the conjecture, where is the problem in the exact sequence?
Oh,
there's some
it's
problem.
It's not exact, right?
Oh,
This is
yeah. Well, yes. Well, that's my question. Exactly, yes, where
it's not exact at the TI. Sorry, you're right.
I see. It's not. The problem is in the middle. In the middle term, proving exactness. Yeah.
Yep.
You know that if you go twice, you get 0. But you don't. I see. Okay. So
that's problem, right. Exactly. Yeah. It's the exactness in the middle.
In the middle. Yeah, I see. That's the problem, in other words.
Yeah, but I want to reformulate it actually as what I said.
Yeah.
Okay. All right.
Hey, I have another question, actually. You say, therefore, variety smooth away from 0. The conjecture has been proved.
Yes.
That would seem to be quite a large class of examples.
Yes, absolutely. It's a huge class. I think recently it's also been shown for some varieties that are not smooth in some isolated points.
Yes, wait. Now
Um,
at zero, I suspect the variety will never be smooth at zero, right?
I suspect that's the case. I suspect that's the case, but I don't know for sure. Let me think about that for a moment.
I think it's very likely the case that it will never be smooth at zero.
Okay. Yeah. Yeah. Probably.
Okay.
Yeah.
All right. Very good. Okay. Let's go.
Okay.
So
Thank
the
you for the
conjecture is
question.
what? What is the conjecture about that variety? The variety what? that you get an essentially normal n tuple of operators if and only if the variety what?
Oh, the conjecture is for any variety, variety coming from a homogeneous ideal. Or in fact, the conjecture is not even coined in terms of varieties. It's coined in terms of homogeneous ideals alone.
So what is the conjecture is what? That this, what is the
For
conjecture?
any homogeneous ideal, you would get essentially normal operators.
Oh, that's the conjecture.
Yeah.
That for any homogeneous ideal, you will get an n tuple of essentially normal.
Yep.
And Douglas refined it to say that it's actually in a Schatten class, that the commutators are in a Schatten class.
Yeah. Yeah. I think that for any time this conjecture has been proven, it's been proven together with some estimate for which Schatten class DOR commutators are in.
Yes.
All right. So suppose omega is a countable set, a subproduct system over, and this is in parentheses, C0 of omega is a family of C0 omega correspondences. If you don't know what these are, don't worry. X equals xn, such that we have the following conditions. 1, x0 is C0 of omega. 2, for all n and m natural numbers, there are co-isometries. U and m from xn tensor xm to xn plus m. These are called the subproduct product maps, such that they behave associatively. So this is un plus m L of u and m tensor IXL is equal to un m plus L IXN tensor UML. Okay, and so I want to immediately say that when omega is just a single point, these are all Hilbert spaces. Okay, and that sort of makes life easier. But I am going to talk about some subproduct systems that are not, where omega is no longer just a single point. Okay. All right. So I think I'm going to skip this. And now I want to define some operator algebras associated to these subproduct systems. Okay, and then give some examples. So given a subproduct system X equals Xn, we may form its Fock space. What is the Fock space of the subproduct system? Is just the direct sum of m equals 0 to infinity of xm. Okay, and as soon as we have a Fock space, we have some creation and annihilation operators on that thing. Okay, so we have creation operators S psi n for psi in xn given by S psi n of eta. That's going to be just take psi, tensor it with eta, and define I think
You are on.
yes, thank you. Sorry about that.
No
To
worries.
have had some technical difficulties. And so we defined the Teplitz algebra of a subproduct system to be as follows. And we can also define the tensor algebra of the subproduct system to be the norm-closed algebra generated by these S psi n's. Okay, and this is for psi and xn, and n, a natural number. Okay, and then this algebra, the Teplitz algebra of the subproduct system, comes with a point norm continuous circle action alpha of the unit circle into star automorphisms of this Teplitz algebra, and it's given by alpha z of S psi n that's equal to Zn times S psi n. And I want to emphasize something here. This algebra, we don't know that it has a universal property. And so the way that we construct a circle action on it is by defining some unitaries on this Fock space such that after we are joined by these unitaries, this is how this action is implemented. This is what these unitaries do. Okay? And so there is no known, at least, universal property for these. Okay? So let's look back at the example, right, that we had of these homogeneous ideals, right? So when I is a homogeneous ideal, let me move on to the next slide, right? So this is homogeneous. Then I can look at the subspace of homogeneous polynomials of degree m, right? And then I will define xi, that's going to be my subproduct system. Xm is just the m in I inside all homogeneous polynomials of degree m. So this is, sorry, I should have added a sub m here. And this is the ortho complement of the homogeneous polynomial. And the subproduct map is given thusly, right? So this is n u and m of P tensor Q. These are two polynomials, other of homogeneous degree m. What this is going to do, so this is just going to be P times Q, right? So the Toeplitz algebra, the Fock space of this subproduct system is exactly f of I that we've seen earlier. The tensor algebra of this subproduct system is exactly this AI, okay? All right, so, you know, already I can tell you something interesting in this regard, that C of the boundary of the variety has alpha invariant, or circle invariant, I should say, quotients and fails. This is an example due to Wieselter, and fails a gauge invariant uniqueness theorem. We'll get to that. Okay, if you don't know what that means, we will get to that. I want to mention a theorem here that sort of classifies the non-self-adjoint algebras in terms of the varieties. And this is a theorem due to Davidson, Ramsey, and Shalit. It says that if I and J are homogeneous radical ideals, then the non-self-adjoint algebras are
Adam, change
isometrically
the page.
isomorphic
Adam,
if
change
and
the
only
page.
if there's
We
a
don't see
unitary.
what you write.
Adam, change the page.
Sorry.
Yep.
Yeah.
Thank you. Is it good now?
Yeah.
Thank you. Sorry. So let me read this again. So I and J are homogeneous radical ideals.
Mhm.
Then the non-self-adjoint algebras are isometrically isomorphic if and only if there's a unitary U from CD to CD that maps one variety to itself. Sorry, to the other. Okay? And the point is that you can sort of get some information about these analytic varieties by looking at the operator algebras. Okay? All right, so this already sort of context of subproduct systems generalizes a very interesting scenario in which there are still many interesting open problems. I'll get to another one shortly. So let's go back to subproduct systems. So let Qn be the orthogonal projection onto the nth summand of my Fock space. So this is the orthogonal projection. Here's the definition due to Wieselter. X, a subproduct system, then the gauge invariant ideal, or the circle action invariant ideal, J sub X, given by S in the Toeplitz algebra, such that the limit as n goes to infinity of SQn is equal to 0. That's an ideal. This is called Wieselter's ideal. and he defines the Kuhn-Pimsner C-star algebra of the subproduct system to be the quotient by that ideal. Okay, this is Wieselter's Kuhn-Pimsner algebra of X. Okay, and so a few remarks are in order. Let's move to the next board now in both. So remarks. 1. Wieselter only worked with essential C-star correspondences, faithful and essential. So he did it more generally than the notion of subproduct systems that I defined here. He did it for subproduct systems over any C-star algebra, but he worked with essential and faithful C-star correspondences, if you know what that means. So if you want to make a comparison to, let's say, Katsura's paper, that you don't need to do because you already have everything in Pimsner's paper in this regard. So there's no issue of Katsura covariance. There's only issues with Pimsner covariance if you want to draw some analog. And indeed, remark number 2, if my subproduct system is just tensor iterates of a single C-star correspondence, then the Teplitz algebra and the Kuhn's algebra of the subproduct system are just Pimsner's Teplitz and Kuhn's algebras. Okay. Now, 3, in the previous example, or examples, I should say, Wieselter's ideal is just the compact operators. It's always the compact operators. Okay. And Wieselter, he asked if his Kuhn-Pimsner algebras have some kind of gauge invariant uniqueness theorem. So that means that as soon as you ask for your C-star algebra to be a quotient of Wieselter's Kuhn-Pimsner algebra in a way that preserves the circle symmetry, then it has to be Wieselter's Kuhn-Pimsner algebra. Okay. But he actually showed in his own paper that a gauge invariant uniqueness theorem can fail. Okay. And so he showed this. He looked at compact operators on the Drury-Arveson space of dimension 2. So you should think of pairs of operators. This is the Teplitz algebra here, and this is continuous functions just on the boundary of the 2-ball. This is a situation where Arveson's conjecture holds. Then C of the boundary of the 2-ball has T invariant quotients. So proper T invariant quotients. And so the issue is, you know, how do we fix that, right? How do we still manage to get a unique quotient in some sense? And then came this paper of Arici and Cod, okay? And in this paper of Arici and Cod, they noticed that you can ask for additional symmetries to be preserved for your quotients, okay? And these additional symmetries, these are these SU2 symmetries, they are very useful in computing the K-theory of the Teplitz and Kuhn's algebras of certain subproduct systems arising from representations of SU2, irreducible representations of SU2. Okay, and I don't know if I have enough time to talk about that, but I just want to mention, I'll write this down. So Arici and Cod showed that SU2 symmetries of subproduct systems enable computations of K-theory.
And how are these symmetries implemented?
Okay, so let me
Adam, may I ask you
say
something?
the following.
Adam?
Let me say the following. Yeah.
I was just asking a naive question. How are these SU2 symmetries implemented? In what sense SU2 is acting somewhere?
Okay, so here's how it goes. You start with, so in order to get this picture of this particular exact sequence, you start with the fundamental representation of SU2. Okay, so that's SU2 sitting inside M2, right?
Okay.
And then what you can do is you can use this representation to construct a subproduct system of
if you are writing,
it's not going to be a subproduct system.
If you are writing, we are not seeing
I'm not writing right now.
Ah, okay.
I'm not writing anything right now.
Okay.
I'm not writing anything right now. So you can sort of create a subproduct system that encodes the representation in some sense. Okay, and that because of the way that you constructed the subproduct system, it's going to have this additional SU2 symmetry. Okay, and of course, you should notice that here the boundary of the two ball is just S3, right? Natural way that SU2 acts on that thing. Also. Okay. All right, and but the point of Arici and Cod is the thing that I really liked about the paper of Arici and Cod is that, this was Wieselter's example. He was saying, okay, continuous functions on the boundary of the two ball doesn't satisfy gauge invariant uniqueness theorem. But if you add the SU2 symmetry, then it is the unique smallest quotient that is still SU2 symmetric. That's really great because it tells you, and so I should say Wieselter asked, I already mentioned that Wieselter asked, is there some kind of gauge invariant uniqueness theorem? And then Arici and Cod, they also asked, is there some kind of SU2 gauge invariant uniqueness theorem? And so what I hope to say or to tell you is that why stop at SU2?
Yeah, this was my question.
Right? Why not just take all the symmetries that you can possibly take on your subproduct system and ask for gauge invariant uniqueness theorem with respect to these symmetries? And I think that that's really the right interpretation for these questions. You have some kind of symmetry on your subproduct system. You take the largest symmetry or enough symmetries on your subproduct system. Does that guarantee a unique quotient that respects these symmetries or is simple with respect to these symmetries? Okay. And that leads us now to subproduct systems arising from stochastic matrices.
And a very nice question, this SU2 symmetry, you could implement it because your D is equal to 2 here. Am I right?
That's right.
Okay.
That's right.
Okay.
Okay, so this, in item 3, this was the example that Wieselter gave to say, oh, the standard gauge invariant uniqueness theorem with a circle action is not enough.
Yeah.
So add some symmetries, right? That's the right thing to do, clearly. All right, so now I want to talk about subproduct systems. And let me change my page because I keep forgetting. Subproduct systems from stochastic matrix.
Question.
Yes.
Is there a universal symmetry of a subproduct system?
Say that again.
Is there a universal symmetry of a subproduct system?
Yes, yes. There's always a group of subproduct systems system automorphisms for any subproduct system.
Okay, thank you. And in
I mean,
this
it's always going to
arithmetic-
contain the circle action, but it
Mhm.
might be bigger, as you could see.
Okay, in this is this Archicad case the case of this universal symmetry?
I think that the way, at least, so I don't know if that's a very interesting question. I think that for the fundamental representation, that should be the case.
Mhm.
But I don't know if it's the same, if it's true for other representations. And that could be, so other irreducible representations of SU2.
Okay,
And if it's not the case, then that's a little dangerous, because then that could mean that the Kuntz quotient would not be the smallest unique one with respect to SU2 symmetries. Perhaps you need to take more, okay? But I don't know, I should say. Okay, so subproduct systems from stochastic matrices. So let me define what a stochastic matrix is, right? So omega, a countable set, a stochastic matrix is a function p from omega times omega into the 0, 1 interval such that the sum of pij over j is equal to 1. Okay, and we denote pij n, that's just going to be the ijth entry of p to the n, right? If you have a stochastic matrix, even if it's on, it's a matrix indexed by a countable set, you can still take products and get another. And we say p is irreducible if for any I and j in omega there exists an n such that pijn is greater than 0. So how should you think about a stochastic matrix? Another way to think about it is that it gives you a directed graph, right? So EP is the set of edges ij such that pij is greater than 0. And that's a directed multiplicity-free graph. And ij is an edge in that graph if there's some positive probability of moving from I to j. Okay? So let's make another definition. P irreducible over omega. The spectral radius.
So omega is now your space of vertices in this graph.
That's right. Omega is my space of vertices, or the state space. I'm going to change that into a group at some point. Okay, and so the spectral radius of P is rho of P. That's just going to be the lim sup of n for the nth root of Pij n. Okay, and that's independent of I and j, actually. Okay. And then I want to define another notion. And so we say a function h from omega to r plus is lambda harmonic for lambda greater than 0 and less than or equal to the spectral radius of P if lambda times h at I, that's equal to P of h at I, which is just the sum of j, Pij, hj. Right? So the value, if lambda was equal to 1, then the value of h at I is an average of values around it. So that's why we call it harmonic. But then it doesn't have to be one harmonic, it could be lambda harmonic. Okay, and then the matrix Q given by Qij is equal to lambda inverse Hj over Hi times Pij is called a dupe transform of P by H, by this lambda harmonic function. So there is some operation here that you can pull off that allows you to change one matrix to another. It changes its spectral radius, for instance. Okay. And now I want to define subproduct systems associated to these stochastic matrices. So this is a definition plus theorem of myself with Markiewicz. From 2014. This is my very first paper. So P irreducible with EP locally finite. I should say that this theorem is a consequence of a theorem of mine with Markiewicz. So locally finite means that every row and every column has finitely many non-zero entries in this matrix. Then I can define a subproduct system. So this is what I'm going to call arv0 of P. It's going to be comprised of arv0 of P sub n, where arv0 P sub n, that's just going to be all matrices Aij in C0 of omega times omega, such that they are supported in the same place, in the same places that P to the n is. So Aij is equal to 0 if Ij is not an edge in the graph of P to the n. Okay? So their support is contained, I should say, in the support of P to the n. And the subproduct map, UNM, and I'm going to simply define it on matrix units because this is C0 of omega times omega, so these are going to be, the linear span of those is going to be dense. So this is Eij tensor Ej prime k, these are the matrix units. This is delta j j prime times the following thing. So this is Pij n Pjk m over Pik n plus m. This is the subproduct map times Eik. Okay, so you should think about it like this. It's matrix multiplication up to applying some weightage. And the weightage is what? If you read this expression closely, you would notice that this is a probability. It's a conditional probability. It's the probability of starting at I. Sorry, it's the probability of going through through the state J at time n, conditioned on starting at I and finishing at k at the n plus mth step. Okay, so that's a conditional probability, really. And so a theorem of mine with Markiewicz from 2014, together with an addition from a paper that I've done with some undergraduate students together with Lyndon.
Next page, maybe.
I'm sorry?
Next page, maybe.
Next
because
page.
we don't
Thank
do it
you.
right.
I appreciate you reminding me all the time. I'm sorry about this. All right. Okay, so let P and Q be irreducible. Then the tensor algebra of these subproduct systems, one of P and one of Q, are isometrically isomorphic if and only if there exists some lambda less than or equal to the spectral radius of P and a lambda harmonic function H such that Q is the Doob transform of P by H. Okay, so the point is this. With Markowitz, we sort of managed to start with, we managed to characterize isometric isomorphisms between these tensor algebras in terms of conditional probabilities. And with the undergraduate students, we managed to give the additional equivalent characterization of coincidence of conditional probabilities with this Doob transform, which is a more natural thing to do, apparently, from the point of view of random walks. Okay. All right. So let's say what these operator algebras are, these Teplitz algebras, these Kuntz algebras. Let's say everything we know about them on concrete Hilbert spaces, right? I don't want to make it difficult with C-star correspondences right now, so I'm going to realize everything on concrete Hilbert spaces with orthonormal bases that I can write down, okay? And this is going to be extremely helpful for purposes of computations. So in our case, the Fock space of R of 0 of P is identified with Hilbert space. I'm not saying exactly what this identification entails, but it's going to be called F sub P with orthonormal basis EJK_M, where JK is an edge in the mth iterate of P, and the creation operators, they're going to be indexed by IJ n, where IJ is an edge in the graph of P to the n, is given by, and this is no surprise, I mean, they are defined using these subproduct maps that you've seen earlier, and they're given thusly. So this is Sijn applied to Ej prime K M. That's going to be delta Jj prime times this conditional probability Pijn Pjk M over Pik n plus M times Eik n plus M. Okay, and then I didn't just define these operators for fun. The Teplitz algebra, which is the Teplitz algebra of this subproduct system, can be identified simply with the C-star algebra generated by these Sijns. So the generators now are far simpler, right? So Ij in E Pn, and n is greater than or equal to 0. Okay, and I just want to mention that I can look at certain subspaces Fpk, which are the closed linear span of Ejk M, where k is fixed now, and jk is an edge in Epm for m greater than or equal to 0. Right, so if you look at the definition of Sijn, you could see immediately that these FPKs are invariant subspaces, but they're in fact reducing. Okay? They are in fact reducing. Okay. So now I want to give you another theorem in which we compute the Wieselter Kuntz-Pimsner algebra for these subproduct systems when the matrix is finite. So this is a theorem with Markowitz. But this is from 2016. So suppose P is finite. And irreducible. Then Wieselter's ideal is simply the direct sum of over states finitely many of compact operators on these reducing subspaces FPK. And we have the following short exact sequence. If you mod out by this ideal, you of course get Wieselter's Kuhn-Spimsner algebra. So I'm just going to tell you what that is, right? I'm going to tell you that that's continuous functions on the unit circle with values in omega by omega matrices. Okay, and I just want to say that this automatically sort of with 6-term exact sequence considerations, it automatically gives you the K-theory for the Teplitz algebra. Okay. So now the question that I want to address next is, what about infinite matrices? Okay, but before I proceed, I just want to say that when P is finite, then the gauge invariant uniqueness theorem does in fact hold. Okay, in this particular scenario. Okay, so any questions before I proceed to start talking about random walks?
So this gauge uniqueness invariance theorem holds without mentioning any big symmetries?
That's correct. No additional symmetries are required. Wieselter's Kuhn-Spimsner algebra in this case gives you the gauge invariant, the unique circle invariant quotient.
Mm-hmm.
Okay.
So
Okay.
just a quick question. When you say P is finite, P is a matrix on omega, right?
That's correct. So omega is finite.
Omega is finite.
Yeah.
Okay, thanks.
All right, Piotr. So now I'm going to start talking about things that are, let's say, working in progress.
Perfect. Working in progress. So let's have the first round of questions.
Yes.
Okay. If you have any questions to what was said thus far, please fire at will. Anybody, any questions? Any further questions?
Yes. Could I come back to this first page of your talk?
The very first page of my talk. Okay.
Yes, yes, at the very beginning.
Yes.
When you are defining this scalar product of
Yes.
monomials,
Yes.
Is this scalar product essential in this construction?
Essential.
For instance, if you replace this scalar product by the scalar product defined by L2 norm on a ball with respect to some natural metric which is invariant with respect to biholomorphism of this ball. Is there a difference in this
yes.
theory?
Yes, there's a difference. I mean, there are all sorts of other kinds of examples like Bergman space and Dirichlet spaces where you can define different weightages and you get different things. It's just that you don't get subproduct systems this way.
I see. Okay. Okay. Thank you.
Yeah.
Anybody else? Another question or comment or suggestion, idea? Okay. If not, so
the interesting part is coming next, right?
Yes, the interesting part is coming next, but it's classified. So we stop recording right now. Okay, you have my clapping hands as a thank you for the first part. And now I stop recording.